Okay, so question number 68 is a methane molecule, and this is the formula, is a methane molecule polar or nonpolar, and how do you know? Well, the first thing we have to figure out is the shape of the molecule. There are two conditions that make a molecule polar. If both conditions don't exist, then the molecule is nonpolar. The two conditions you have to have is an uneven arrangement of bonds. That's the first condition. And the second condition is polar bonds. If you don't have both of those, the molecule is nonpolar. So let's start, and you can start with either one. You can start with determining whether or not the bonds are polar, or you can start with determining whether or not the molecule is unevenly arranged. Let's start with whether or not the bonds are polar. For that, we need to know electronegativity. Now for CP chemistry classes, you can use the periodic table of oxidation or electronegativities, okay? Honors classes have to know the pattern and figure it out, and we'll discuss both of those here. So carbon has an electronegativity of 2.55. So carbon, the electronegativity for carbon is 2.55. The electronegativity for hydrogen is 2.1. If we subtract those, we get the electronegativity difference. So we have a bond between carbon and hydrogen, and we're looking for the electronegativity difference, or END, for this bond. And so when you subtract the two, you get 0.45. But as you can see, there's an empty slot right here. And so that means this 5 needs to be rounded off. And so our electronegativity difference for carbon to hydrogen bond is really 0.5. Okay? Well, that's right on the border between being polar or nonpolar. It's more on the polar side than the nonpolar side, but it's hard to say for sure. So let's make sure we also double check this against the shape of the molecule. So for that, we start with the electron dot formulas. Carbon has 4 electron dots, and hydrogen has 1. Now the way you know that is to look at your periodic table. I'm using the CP test references. Honors is very similar, but their atomic masses are a little bit different. But carbon is right here, and so if you back up on this row, we see we start with lithium 1, beryllium 2, boron 3, and carbon 4. So that means I have 4 electrons in this second primary level, and that's what these dots all mean. Hydrogen is in column number 1, so it only has 1 electron in its outer level. So I can share these 2 electrons here. When you share 2 electrons, hydrogen has all the electrons it needs or wants. But I need more hydrogens for carbon because carbon needs 8. Most atoms want to have that magic number 8. It's called the Octet Rule. And so I want to keep putting more hydrogens around here until I get to the point where carbon has all 8 electrons that it wants. Okay, and so we have a sharing arrangement now. We started with the electron dot formulas, now we have a sharing arrangement. So from this, then we're going to draw a Lewis dot formula where we take the shared pairs of electrons. So these electrons we have circled and shared then to show that they're shared. We're going to push that whole thing together and put the 2 electrons side to side. So with that bottom set right there, they become side to side like this. With this side set, they become side to side in this manner. Okay? And over here like this, and up here like this. Okay? So that's the Lewis formula. Now we don't have to write the this is the Lewis dot formula. You don't have to write the Lewis formula to get the molecular shape. All we have to do is identify the number of sets of electrons around a central atom. A set of electrons is the total number of electrons that are shared between 2 atoms. So I've got 2 electrons shared between these 2 atoms, and 2 electrons shared between these 2 atoms, and 2 here, and 2 here. That's 4 sets. Now a set could have 4 electrons, or could have 6 electrons, if those electrons are all shared between 2 atoms. In this case, we only have 2 electrons in the shared sets. So from this, then, we're going to draw a three-dimensional shape that shows how we arrange 4 sets of electrons in such a way they'll be as far apart three-dimensionally as we can get them. For that, we need a tetrahedral. So one set of electrons is going to go vertical. One set of electrons is going to swing down 109.5 degrees. Another set of electrons is going to swing out away from the paper toward you. And then the last set of electrons is going to swing back behind the paper. And so we draw those like this. The triangle means they're coming out toward you. The dotted line means they're going back behind the paper. And so this is a three-dimensional arrangement of electrons around a central atom. These 4 electrons here. This is called the electron pair shape, and the three-dimensional shape, the way we arrange these in three-dimensional space is called the tetrahedral. So this is a tetrahedral electron pair shape. Okay? The geometry is tetrahedral. The kind of drawing we have is electron pair shape. Now, the next step is to see, look at the number of these pairs of electrons. Figure out how many of them are lone pairs or how many of them are shared pairs. Any of them that are shared between 2 atoms are called shared pairs. And the shared pairs get replaced in this next drawing with the atom that belongs there. So because this pair of electrons here is shared between carbon and hydrogen, this pair of electrons is going to be eliminated in our next drawing, and we're going to replace it with a hydrogen. So here's a carbon, and there's a shared pair to a hydrogen, there's a shared pair to another hydrogen, a shared pair coming out away from the board toward you to a hydrogen, and a shared pair going back behind the paper to another hydrogen. Okay? So what we have here is called a tetrahedral molecular shape. So the shape of the molecule is a tetrahedral. There were no lone pairs, so without any lone pairs at this point, this is the end of the drawing arrangement. Because we don't have any lone pairs, this molecule has an even arrangement of bonds, so that we don't meet the second condition. Remember, we have to have 2 conditions. We have to have polar bonds. We weren't so sure about whether this was going to be polar or not, so that was kind of an iffy situation. But with this, these are evenly arranged. So no matter whether or not this is a polar bond or not, it wouldn't matter. If you don't have both conditions, polar bonds and an uneven arrangement, you don't have a polar molecule. So because this is evenly arranged, it cannot be, regardless of the polarity of the bonds, it cannot be a polar molecule. So the question is it a polar molecule? The answer is no, it's non-polar.